when 1 mole of ionic compound dissociates into its respective ions in its gaseous state, how much energy is required for that dissociation? That is called as lattice enthalpy. Phase transformation means from one state to another when it is converting. The enthalpy change associated with it is called as enthalpy change in phase transformation. 1 mole of a substance, when it dissolved in a specific amount of solvent, the enthalpy associated with it is called as enthalpy of solution. Hello everyone, this is Amli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 5 of the chapter Thermodynamics. So in the last session, we studied about how you can measure the value of change in internal energy as well as change in enthalpy, right, using calorimeter, and the apparatus and how we do the experiment, all that we have studied in the last session. And then we also studied thermochemistry, that is thermochemical equations, how to represent it, and all that we have studied in the last session. So in today's session, we are going to study enthalpy of solutions, right, and lattice enthalpy. What is lattice enthalpy? And enthalpy change during phase transformation. Phase transformation means from solid to liquid, either to liquid to gas or gas to solid, all of that. Changes from one state of matter to another state, right? And the last one is Hess's law of constant heat summation. Okay, so all this we'll study in this session, and thereby we'll end it with few numericals also. Okay, so let us begin with the first one, lattice enthalpy. So lattice enthalpy, we have already studied what it is in chemical bonding and molecular structure chapter. So you already have an idea about lattice enthalpy. We have already studied about what is Born-Haber cycle, the different steps of that. So let's quickly refresh that as well here. So the lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. Okay, so when 1 mole of ionic compound dissociates into its respective ions in its gaseous state, how much energy is required for that dissociation? That is called as lattice enthalpy. So let's take 1 mole of sodium chloride here. It gets dissociated into Na plus, that is a cation, and Cl minus is the anion. So this enthalpy which is required for this process is called as the lattice enthalpy. It is called as the lattice enthalpy, and the value is plus 788 kilojoule per mole. So you're already familiar with lattice enthalpy. So let's take the example of Born-Haber cycle here, right? So in Born-Haber cycle, we know that, yes, from Na plus and Cl minus, we are going to form sodium chloride, right? So one more point that you have to remember is lattice enthalpy, either it can be the energy which is required or the enthalpy which is required to break 1 mole of ionic compound into its constituent gaseous ions, or else from the constituent gaseous ions we can form 1 mole of ionic compound. That is, from Na plus and Cl minus we can form NaCl, the energy which is required to form this, or else from NaCl we can form Na plus and Cl minus, the energy required for that. Either ways we can consider. Okay, so the steps involved in Born-Haber cycle, the first one is sublimation of sodium metal. So the first step is sodium metal will be in the solid state, it gets converted into gaseous states. So that is enthalpy of sublimation, from solid directly to gaseous state. That process is called as a sublimation, right? So the energy associated with that is called as enthalpy of sublimation, and the value is 108.4 kilojoule per mole. The next step is the ionization of sodium atoms. That is, which energy or which enthalpy is associated with it? It is ionization enthalpy. That is, sodium in gaseous state now gets converted into Na plus and releases 1 electron, right? It loses 1 electron. So it is that energy which is required to remove 1 electron from the sodium atom is called as ionization enthalpy. The value is 496 kilojoule per mole. The next one is the dissociation of chlorine. The reaction enthalpy is half the bond dissociation enthalpy. That means now it is chlorine gas. We need the chlorine atom here. It is Cl2 here, we need Cl. Okay, so it is half Cl2. So the half of the bond dissociation energy we have to take. So the value is 121 kilojoule per mole. Right. The next one is the electron gain enthalpy. Electron gain enthalpy means the energy which is associated when, or the energy which is released when 1 electron is gained by the atom. So we have chlorine atom here. Now the chlorine atom accepts 1 electron and forms an anion, that is Cl minus anion, and the energy That is called as the electron gain enthalpy. It is minus 348.6 kilojoule per mole. Why it is minus sign? Because energy is released. So it is a negative value. The electron is accepted, hence the energy will be released. And the last one is lattice energy. That is Na plus and Cl minus combines to form NaCl. So you got the Cl minus in this step, as well as here you have found the Na plus also. So now this Na plus and Cl minus will combine and form NaCl. So I hope that is clear for you. So these are the various steps happening. So all together we can write the sequence of steps is shown and is known as the Born-Haber cycle. So all together the steps we have discussed now, it can be sequentially written like this, and this cycle is called as Born-Haber cycle. The importance of the cycle is that the sum of the enthalpy changes round a cycle is 0. Okay, so if you take the sum of all of these energies, you will finally get it as 0. Okay, so now we are going to apply Hess's law here. Now what is Hess's law? We will be studying in the upcoming slides in this session itself. Okay, so according to Hess's law, if you have to calculate the lattice enthalpy, what is that we have to calculate here? It is a lattice enthalpy. So if you take the sum of all other enthalpies here, you can calculate the lattice enthalpy. Okay, so what is the exact definition for Hess's law? We will study now. So as of now, you can understand that lattice enthalpy, if we have to calculate, we have to add or take the sum of each of the enthalpies in each step. If we add it, we can get the enthalpy of the total process, right? So as you can see here, the lattice enthalpy will be equal to this value, that is the enthalpy of sublimation, and then ionization enthalpy, right, and then enthalpy of dissociation, and electron gain enthalpy or electron affinity also you can call. So if you take the sum of all this, you will get the value of lattice enthalpy. So as you can see here, 411.2, that is the enthalpy of formation of sodium chloride. Then 108.4, that is the enthalpy of sublimation. 121, that is enthalpy of dissociation. 496, that is ionization enthalpy, and minus 348.6, that is the electron gain enthalpy. So altogether, if you add all the enthalpies associated with all the steps, you will get the lattice enthalpy, which is plus 788 kilojoule per mole. Okay, so I hope that is clear for you. So this is lattice enthalpy and how we can calculate it using all the other enthalpies which is associated with the reaction. Now moving on to the next one, that is enthalpy of solution. Okay, enthalpy of solution. Let us understand what is enthalpy of solution and let's see how we can calculate it as well. So enthalpy of a solution of a substance is the enthalpy change when 1 mole of it dissolves in a specific amount of solvent. So 1 mole of a substance, when it dissolves in a specific amount of solvent, the enthalpy associated with it is called as enthalpy of solution, right? Okay, so when an ionic compound dissolves in a solvent, the ions leave their ordered position on the crystal lattice. Okay, that means if an ionic compound is present and we are dissolving it in water, means from solid state it is getting converted into liquid state, right? So in that case, the ions can freely move. In that case, solids, they will be tightly packed. Now when they are getting converted into liquid, they can easily move around. So these are now free in the solution, right? But solvation of these ions also occurs at the same time. So that means that enthalpy of hydration, hydration means when we are dissolving it in the solution or the solvent, that enthalpy as well as the enthalpy related to solvation also we have to consider to calculate the enthalpy of solution. So solvation means the hydration in case of solvent is water. Okay, if it is in the case of water. Now, so as you can see here, this is the ionic compound we have taken. Okay, so if you have to calculate the enthalpy of solution, okay, so first what happens is lattice enthalpy associated with it. That means AB get converted into its corresponding or constituent ions, that is A plus and B minus. So the energy or the enthalpy which is required to convert 1 mole of ionic compounds to its constituent ions is called as lattice enthalpy, right? So we can calculate lattice enthalpy. Now these are in its gaseous state. Now we are going to dissolve it in a specific amount of solvent. So what happens? That is called as the enthalpy of hydration, right? So now you will get the A plus and B minus ions in aqueous states. So if you take the sum of lattice enthalpy and hydration enthalpy, we can calculate the enthalpy of solution. So I hope that is clear. So let's see. The enthalpy of solution of AB in water is therefore determined by the selective values of lattice enthalpy and the enthalpy of hydration of ions. So in the first step, the AB will get dissociated in A plus and B minus. That is the lattice enthalpy. Now they are in gaseous state. After hydration, they will be converted into the aqueous state. So that is the hydration enthalpy. So altogether, the enthalpy of solution can be calculated by the sum of lattice enthalpy and hydration enthalpy. So I hope that is clear. For most of the ionic compounds, the enthalpy of solution is positive and the dissociation process is endothermic. Therefore, the solubility of most salts in water increases with rise of temperature. So when the temperature increases, the solubility of the substance also increases in water. So generally it will be a positive value and it will be an endothermic process. If the lattice enthalpy is very high, this point, if the lattice enthalpy is very high, the dissolution of the compound may not take place at all. So you have to remember that point as well. If the lattice enthalpy is very high, then the dissolution will not take place. So I hope lattice enthalpy and enthalpy of solution is clear. Now moving on to the next one, enthalpy changes during phase transformation. So as I told you in the beginning of this session, phase transformation means from one state to another when it is converting. The enthalpy change associated with it is called as enthalpy change in phase transformation. That means from solid to liquid, liquid to gas or gas to solid. Okay, so first one is standard enthalpy of fusion or molar enthalpy of fusion. So what is fusion? You already know that it is the conversion of solid into liquid state. So the enthalpy change that accompanies melting means solid to liquid, right? Melting of 1 mole of solid substance in standard state. This is important. Okay, in standard state is called as standard enthalpy of fusion or molar enthalpy of fusion. Why it is called molar enthalpy? Because we are talking about 1 mole of the substance. So it is an enthalpy change. Okay, it is an enthalpy change which happens when 1 mole of a solid is melted. Okay, it is the melting of 1 mole of solid substance. How much enthalpy change is accompanied with it? Okay, and another important point, it is standard enthalpy of fusion. So it must be in its standard state. Okay, so you can write it at delta fusion and H naught. That 0 stands for the standard conditions. So as you can see here, water in the solid state, that means ice is getting converted into water in liquid states. That is the normal water. So the enthalpy of fusion is given as 6 kilojoule per mole. Okay, now that is the first one. Now next one is standard enthalpy of sublimation. So from standard enthalpy of fusion, you can yourself derive what is standard enthalpy of sublimation. So it is the enthalpy change accompanied when, yes, the substance is getting converted from solid to gas, right? So let's see, the standard enthalpy of sublimation is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure. Okay, so 1 mole of a solid substance in its standard condition. Okay, that means 1 bar pressure and constant temperature. When it sublimes, the enthalpy change associated is called as standard enthalpy of sublimation. So as you can see here, carbon dioxide is in the solid state, that is called as dry ice. It is getting converted into carbon dioxide in gaseous state. That is, sublimation process is taking place and the enthalpy of sublimation is 25.2 kilojoule per mole. Next one is sodium in the solid state getting converted into sodium gaseous state. That is also sublimation and the enthalpy of sublimation is given here. So I hope that is clear. Now moving on to the next one, that is standard enthalpy of vaporization. Now what is vaporization? Yes, from liquid state to gaseous state, right? So amount of heat required to vaporize 1 mole of a liquid at constant temperature and under 1 bar pressure. Okay, under standard condition, the enthalpy change which is required or the enthalpy change which is happening when 1 mole of a liquid is getting converted into its gaseous state, right? It is called as standard enthalpy of vaporization or else molar enthalpy of vaporization. Molar because we are talking about 1 mole. right? So it is represented in this form. So as you can see here, water in liquid state getting converted into water vapor, that is called as enthalpy of vaporization, and it is 40.79 kilojoule per mole. So I hope standard enthalpy of fusion, standard enthalpy of sublimation and standard enthalpy of vaporization is clear for you. So as you can see here, the name standard suggests that this will happen in standard conditions. Okay, now moving on to the next one. So now moving on to the next important law, which is called as Hess's law of constant heat summation. Okay, so let's read the statement here. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of standard enthalpies of the intermediate reactions into which the overall reactions may be divided at the same temperature. Or the heat change that take place in a chemical reaction is independent of time taken and number of intermediate steps involved. So that means that the total enthalpy of the reaction can be calculated even if the reaction is taking place in several steps. The total enthalpy of the reaction can be calculated by taking the sum of the enthalpies of each of the intermediate steps. Okay, I hope that is clear. So if the reaction is taking place in several steps, okay, we have discussed it in Born-Haber cycle also. It is taking place in several steps. So if you take the sum of enthalpies of each of the steps, take the sum of that, you will get the total enthalpy of reaction. So that is called as Hess's law of constant heat summation. So let's take an example and understand this, how exactly we can calculate it. So here you can see that carbon is combining with half O2 and forming carbon monoxide. So we have to calculate the enthalpy of the whole of this reaction. But we don't know the value for this, and how do we calculate it? Okay, so we have to calculate this using another two equations, that is the enthalpy of the reactions which we already know. So now the one of the reaction is carbon and oxygen gives carbon dioxide. So the enthalpy of this reaction, that is enthalpy of formation of this particular reaction, is minus 393.5 kilojoule per mole. Okay. So this is the value of this particular reaction. Okay. So that is carbon plus oxygen gives carbon dioxide. Now carbon monoxide can combine with half O2, okay, and form carbon dioxide. And this is another reaction. The enthalpy of formation of this particular carbon dioxide, of this particular reaction, in which the enthalpy of formation of carbon dioxide is minus 283 kilojoule per mole. Okay. So these two reactions, enthalpy of formation or enthalpy of the reaction, we already know. So in such case, we have to calculate the enthalpy of reaction of formation of carbon monoxide. Here in the product it is carbon monoxide, but I have carbon dioxide here. So what we have to do is we have to rearrange the equation in such a way that we obtain the product and the reactants in the way we want. So that means that we have the carbon monoxide in the product side here, and in the two reactions, the enthalpy of reaction which we already know, the carbon monoxide is in the reactant side. So what I can do is I can reverse this particular reaction. So if this is my first reaction and this is my second reaction, I reverse this second reaction. So that means I'm going to write carbon dioxide in the reactant part and carbon monoxide plus half O2 in the product side. So if I'm reversing this reaction, some change should be happening to the enthalpy also, right? So the enthalpy of the reaction will become, instead of minus, I have reversed this. So this will become plus 283 kilojoule per mole. Okay. So now I got two values here. Okay. So one is carbon plus oxygen giving carbon dioxide. The enthalpy is given. And the next one is carbon dioxide giving carbon monoxide plus half O2. Enthalpy is given. Now what I am going to do is, this is the first equation, this is the second equation. We are going to do 1 plus 2. We are going to add these two reactions. Okay. So this particular reaction I have reversed it and I have got this reaction. So this is my first one, this is my second one now. So I am going to add these two. So as you can see here, carbon is here. Okay, is there any other carbon in this reaction? No. So one O2 is here, another half O2 is in the product side. So if I add it, means I am subtracting it from each other. One is in the reactant side and another is in the product side. So what happens? O2 and half O2. If I subtract it, I'll get half O2, right? So I write in the reactant side carbon plus half O2. Okay, so what happened here? This O2 and this O2 gets cancelled, only half O2 will remain. Now what else is present in the reactant side? Yes, carbon dioxide is here, but in the product also you have carbon dioxide. So those two will get cancelled. So now what else is remaining in the product side? Only carbon monoxide. Right. So I got the equation. Yes, as you can see, carbon plus half O2 giving carbon monoxide. And also you have to mention their states, right? So this is in the solid state, gaseous state and gaseous state. So finally I obtained this equation. So what is that we did till now? We know the enthalpy of formation of the first reaction and second reaction, and I added that and I got the reaction that we want. Okay, so just by adding the enthalpy of the reaction of the first one and second one, I can get the enthalpy of reaction of the reaction that we want, that is minus 393.5 plus 283 kilojoule per mole. If I do, I get the value as minus 110.5 kilojoule per mole. So this is how you have to calculate the enthalpy of the reaction. Okay, so this is the application of Hess's law of constant heat summation. That means the reaction will happen in different steps. So if you take the sum of enthalpies of each of that, you can get the total enthalpy of the reaction. Okay, so now let's do few numericals and you'll get a better idea of this. So let's take the first example. Calculate the enthalpy of combustion of liquid benzene, given that the enthalpy of formation of benzene, carbon dioxide and water are respectively. So the enthalpy of the reaction that we have to calculate is the enthalpy of combustion of liquid benzene. Okay, so the reaction we require here is C6H6 in the liquid state. Combustion means what? Oxygen, right? Combustion means it is burning in the presence of oxygen, and it gives what we already know, that combustions, the products are carbon dioxide and water. So now we have to balance it. So it is C6H6 here. So I make this 6 and 3 and this becomes 15 by 2. So this is how I balance the equation. So already you are familiar with how to balance the equation. So this is the reaction that is happening here, and the enthalpy of this reaction is what we have to calculate. But we don't know the value of this. But we do know the enthalpy of reactions of other reactions which are given here, that is the enthalpy of formation of benzene. So the first one is given, the enthalpy of formation of benzene. So how benzene is formed? Carbon plus hydrogen will give you C6H6. So to balance it, 6 here, 3 here. So it becomes C6H6 is a balanced chemical equation. And the enthalpy of this particular reaction is already given, that is 48.51 kilojoule. This is already given, right? Now moving on to the next one, that is enthalpy of formation of carbon dioxide is also given. So you need to be knowing the equations for the formation of carbon dioxide, formation of water, formation of benzene, all that. Okay, so the next one is carbon plus oxygen will give you carbon dioxide. So this is already a balanced chemical equation. So the enthalpy of this reaction is also given as minus 393.5 kilojoule. That is already given. Now the next one is enthalpy of formation of water. That is also given. So you know hydrogen plus half O2 gives H2O. Okay. So when we balance this equation, you get it. Hydrogen plus half O2 gives H2O. And this enthalpy is already given, that is minus 285.83 kilojoule. So these three values, enthalpy values, are given in the problem itself. Okay, but we need to write the equation for ourselves. So these three reactions are given, and using these three, now we are going to end up in the first equation. So just by adding the values, you have to reach that. But these three equations are not similar as the equation or the reaction we want. So we make up it in that way. So let's see. So as you can see here, C6H6, that is your benzene, is in the reactant side. Okay, but here you can see the benzene is in the product side. So what do I do with the first reaction? The first reaction, you can see here, I am going to reverse it. So C6H6 comes here and this comes to the other side. I am going to reverse this. So what happens to the enthalpy of the reaction? It is plus 48.51. Now it becomes minus 48.51. So I am going to write that here. So I am going to write that particular reaction here. That is C6H6 gives 6 carbon and 3 H2. Okay, just reverse the reaction. So the enthalpy now becomes minus 48.15 kilojoule. Any doubt in this? I hope it is clear. Now moving on to the next one. Carbon plus oxygen giving carbon dioxide. So carbon dioxide is in the product side and carbon dioxide is still in the product side. But as you can see here, carbon dioxide, there are 6 molecules. Okay, or 6 moles of carbon dioxide. So I multiply the second equation by 6. Okay, so I'm going to write that equation here. Now I'm multiplying the whole of this equation by 6. So this becomes 6 carbon atom plus 6 oxygen gives 6 carbon dioxide. And the enthalpy of the reaction will become what? Multiplied by 6, right? So that is minus 393.5 into 6 kilojoule. So you have to multiply that value there as well. Now moving on to the next one, H2 plus half O2 giving H2O. Now as you can see here, here also it is in the product side, here also it is in the product side. So you need not reverse the reaction, but you can see here there are 3 moles. So what do? I multiply this particular reaction by 3. So the reaction becomes 3H2. Now there is 1 by 2 into 3 I am doing. So it becomes 3 by 2 O2. And it gives 3H2O. So what happens to the enthalpy? Again it is minus 285.83 multiplied by 3 also I have to do. So the whole equation you have to multiply it by 3. So this is what I have obtained here. So we have reversed it and multiplied with whatever value we require. Now we are going to add each of this. This is the first equation. This is the second equation. This is the third equation. Now we are going to add 1 plus 2 plus 3. So what happens here? This is the 3 reactions that we require now. Okay. So C6H6 is here. Okay. Nowhere else you can find the benzene. Okay. Now moving on to carbon. Here the carbon is in product side. Here the carbon is in reactant side. So it cancels out with each other. Now you can see 3H2 here, 3H2 here. That also get cancelled out. Now you can see 6O2 here and 3 by 2 O2 here. And both are on the reactant side. So what do we have to do? It doesn't cancel out. You have to add it. So what is 6 plus 3 by 2? It will be 15 by 2. That is your reaction itself. Right. So 15 by 2 O2. I am adding these two. That is 6 O2 and 3 by 2 O2. You will get 15 by 2 O2. Now what else is there? This part is done. Now you have 6 carbon dioxide and 3 H2O. That is what you can see here. So finally you obtain the equation that you want. Okay. So what is that? You are going to get C6H6 from here. The carbon and H2O is cancelled out. The 6O2 and 3 by 2 O2 I added. I got 15 by 2 O2. So that means that if I add these 3 values, that is the reaction enthalpy of the first one, second one and third one, these 3 values I add, I'll get the answer for the reaction which I require, and the enthalpy of the reaction which is required. This reaction, we obtained it from the whole of this each step, right? So the enthalpy of the reaction is calculated as minus 3267 kilojoule per mole. So I hope this is clear. So when you are adding this multiplied by 6 and multiplied by 3 also you have to include. So finally you will get that answer. So I hope it is clear. Now moving on to the next numerical. Calculate the enthalpy of formation of methane from the following data. So the reactions is already given to you. Carbon plus oxygen giving carbon dioxide. The enthalpy is given. Hydrogen plus half O2 giving water. Enthalpy is already given. And the next one is methane plus 2O2 giving carbon dioxide and 2 molecules of water. Enthalpy is given. So the 3 reactions from which we have to calculate the enthalpy of formation of methane is given. Okay. So now what is the reaction that we require? That is enthalpy of formation of methane. That means carbon plus hydrogen will give you CH4. This is the equation that we have to end up with. So I balance it. This is the equation. So we have to end up in this equation. So let's take these 3 equations and let's see what all rearrangements we have to do here. So carbon is in the reactant side here. You can see its carbon is in the reactant side itself. And next moving on to the next equation, that is hydrogen. Hydrogen is in the reactant side again, no problem. But it is 2 molecules of hydrogen. Okay, 2 moles of hydrogen. So I multiply this equation by 2. Okay, so I am writing down each of this equation again. That is carbon plus O2 giving carbon dioxide. That equation remains as it is. Now the second one I am going to multiply 2H2 plus 2 into half is 1, right? So O2 will give H2O. So this becomes my second equation. Now moving on to the third one, CH4. Methane is in the reactant side, but I need methane in the product side, right? So I am going to reverse this reaction. So this comes here. So the equation becomes CO2 plus 2H2O giving CH4 plus 2O2. So what happens to the enthalpy of the reaction? It is minus here, it becomes plus, right? So the enthalpy of the reaction becomes plus 890 kilojoule. Now what happens to the enthalpy of the second reaction? As you can see here, I have multiplied by 2. So the enthalpy also I have to multiply, that is minus 285.87 into 2 I have to do. And the first one remains the same, that is minus 393.5 kilojoule. So I hope till here it is clear. Now we are going to cancel out each of this which is not required. So as you can see here, carbon, there are no other carbon here. So no problem. Now moving on to oxygen, you have one O2 here, 2 O2 here and 2 O2 on the product side. So these two becomes 2 O2 and this is another O2 cancelled out. Now moving on to the next one, that is one carbon dioxide in the product side, one in the reactant side, cancelled out. Now moving on to the water, it is 2H2 here, here also it is 2H2O, because as we have to multiply the whole of this equation by 2, here also it becomes 2H2O. It's just H2O multiplied by 2, here also it will be 2H2O. So this 2H2O, this 2H2O, product and reactant side, that also will get cancelled. So finally what is remaining here? Carbon plus 2H2 will give CH4, right? Carbon plus 2H2 will give CH4. So we ended up in the equation that we require. So you have to mention the states also, carbon in solid state, hydrogen gaseous state and methane in gaseous state. So all this you have to mention. So that is the thermochemical equation. So that means that if we add all of these values, the enthalpy of reaction of the first equation, so this is your first equation, right? This is second equation and this is the third equation. So if you add all of these values, you will get enthalpy of the whole of this reaction. That is the formation of methane, this particular reaction. So the enthalpy of the reaction, if you add all of this three values and don't forget to multiply it by 2 and reverse the sign, right? So the final value will be minus 75.16 kilojoule. Okay. So this is how you have to do the numericals based on it. So I hope it is clear. So how you have to do is either the reactions will be given corresponding, the enthalpies also will be given, or else just the enthalpies will be given associated with the reactions. You yourself have to write the reactions, which we have done in the previous question. And just by rearranging it, okay, we write down the reaction that we need first, and then from the reactions which is given, we just rearrange the values. Okay, rearrange means either multiply it by 2 or reverse the reaction, whichever is required. You require it in the product means reverse the reaction. So when you are reversing, change the sign in the enthalpy of formation also. And then finally, other unwanted products and reactants you can cancel out, and then you will finally obtain the equation or the reaction that you require. So just by adding the values, you can finally obtain the answer. So I hope how to calculate the enthalpy of the reaction using Hess's law of constant heat summation is also clear for you. So in the next session, we are going to study about spontaneity of the system. So I hope the topics we have discussed in this session is clear for you. So that's all for today. Thank you.